Welcome to Sergio's Structural Engineering channel. Today, I would like to discuss with all of you how to design a earth retaining wall. Today, we are going to concentrate our efforts to study how to determine the horizontal lateral pressures and how to deal with the balance conditions in terms of sliding and overturning. Okay? Do you want to come with me? Let's start. In order to explain how is the lateral pressure against any lateral retaining structure, it is interesting to fix our attention to the behavior on the earth and the water. Let's start with the water. As you can see at the sketch located at the left side of the image, we can find here a differential element, okay, of water located at a depth of C. As you can see in this balance or free body diagram, the pressure of the water, vertical pressure of the water, is equal to the density of the water multiplied per the depth when we are studying this differential element. In accordance to vertical equilibrium, the pressure located at the bottom of the differential element should be the same, but in the opposite direction of the pressure that we have obtained before. According to Pascal's principle, in this case, the pressure applied in the horizontal direction is the same as the vertical one. If we want to describe this hydrostatic behavior of the material in a, let's say, gentle way, we have a stress tensor in which the main diagonal of these matrix elements, we can find the normal stresses in the main global axis. The rest of the positions of this matrix are zero. And you can see here those elements are located for different tangential stresses. Which are the values for those for this differential element located in the diagonal? Are all of them in the three main directions are the same, are equal to the density per the depth to be studied. Let's fix our attention to the Earth. Okay. Now we are going to generate the same equilibrium forces. Let's concentrate to these differential elements. As you can see, vertical pressure over this portion of the soil should be the density of the soil multiplied by the depth in which are creating this balance. Of course, in terms of balance, sigma V is going to be the same. Soil multiplied by C. But because of the soil has a certain shear stress and tangential stress, horizontal pressures are not, they don't have the same value as the vertical ones. We can then establish a linear relationship between the horizontal pressure and the vertical pressure. Okay, this linear relationship between the horizontal and vertical pressure, it is called a coefficient of lateral pressure. Okay, and in accordance with the research and with the theory, there are three values: K0, rest condition; Ka, active condition; and Kp, passive conditions. Today, we are going to focus only in the active coefficient of lateral pressure, because of is the one that we are going to use to determine the lateral pressures against our retaining structure. Once we have a knowledge that Earth can generate some kind of lateral pressure against any of our retainer structure, it is necessary to identify which are those parameters that generates that horizontal forces. For lateral pressures, we have mainly three parameters to be defined. The first of one is the internal friction angle, defined by the Greek letter phi, normally measured in degrees or in radians. We also have the density of the soil, identified with the Greek letter gamma, okay, and the typical units of density. In this case, for example, continuity divided by a cubic meter. And cohesion, normally defined with the the capital letter C. Um, the value is typical associated with clays, and the units normally in terms of pressure or stress. Okay. Internal friction angle, it is can be determined if we drop some amount of soil over a flat surface, then it will be generated a cone. Okay, the edge of the cone, or the inclination between the edge of the cone and the horizontal flat, that inclination is called the internal friction angle. As much bigger the internal friction angle, as much friction there is between the particles that compose the soil, and therefore less lateral pressure against any structure. Uh, for the soil density, there is nothing to do less than measure the mass of amount of soil divided by the volume. Cohesion, it is quite difficult the factor to be explained. It is clearly associated with the clays and is like a chemical interconnection between little particles that compose that type of soil. Also, water is involved in these connections, and as I said, typical behavior for clays. There are two major classifications. Of course, there are others, intermediate materials, soil materials, but mainly we are going to deal with sand and clay. In terms of lateral pressure, sand could be defined only with internal friction angle and gamma for soil density, and it is defined like a cohesion is always zero. Um, um, in the opposite way, clay, of course, has friction angle density, but cohesion could be reached from very low values up to higher values. Monsieur Coulomb was an army French civil engineer which developed a great number of achievements in terms of structural engineering. Coulomb was the first to develop the concept of active soil pressure coefficient, called Ka. As you can see in the sketch located the left side of the image, the very complex theory of Mr. Coulomb was taking into account all the a great number of parameters, like for example the slope of the rain located over the top of the retaining wall, but also the possibility to generate some kind of vertical friction between the outer face of the retaining wall and the wedge of the soil to be sustained or to be retained. Okay, all those parameters was concentrated in that complex equation located at the bottom right side of the figure, uh, where it was identifying the internal friction, the internal friction angle, the delta phi, the relationship in terms of friction between the outer side of the wall, and vita, the slope of the soil, of the top of the retaining wall. Also, we can find here in the image equation for sigma prime A, which includes the terms of a cohesive term added by engineer Bell during the 20th century. All those soils which has been identified with cohesive for sure generate less lateral pressure than others with cohesion equal to zero. During the erection of the Eiffel Towers, the French nation decided to grant Mr. Coulomb for his contribution not only for the electrical well-known work, but also for his achievements for the structural engineering field. If you have the chance to visit Paris and get closer to this wonderful structure, you can also read other important names related to structural engineering, like Tresca, Poisson, Navier, Vicat, Polonceau, known by his trusses, or Lamé. Another way to determine active coefficient for lateral pressure is to use the Rankine theory. Mr. Rankine was a Scottish mechanical engineer who was developed a great number of achievements, and breakthroughs in terms of engineering and scientific, although he lives only 50 years. As you can see, the equation for the active coefficient lateral pressure, the equation is clearly less complex than the Coulomb equation explained just a minute ago. The simplicity of the equation is based in two assumptions. The first one, it is that delta divided by phi is equal to 0. It means that there is no friction assumed to be generated between the outer part or outer face of the retaining wall and the soil to be sustained. And the second assumption, it is that the slope of the earth located at the top of the retaining wall, it is 0. The equation, the simplicity of the equation, it is very helpful and useful in order to be used for quickly check-ins or to define in an easy way the lateral pressure to be applied to a retaining wall. Let's develop a practical example to explain all the concepts previously treated in this post. Okay, on the left side here we have a L retaining wall, okay, of concrete. The aim of this retaining wall is to retain sand earth with the following properties and parameters: a density of 18 kilonewton by cubic meter, internal friction forces over the soil of 28 degrees, and cohesion 0 as it is assumed sand. This is also important in the designs to take into account a surcharge located at the top of the soil, the top of the retaining wall, normally equal to 10 kilonewton per square meters. The value it is also reflected in the bridges design codes, and it is very common to be used during the design of the bridge abutments. Okay, the first thing we have to do is to determine or to calculate the active coefficient earth pressure using the values of Rankine in accordance with the friction angles. The value is equal to 0.36. I'm sorry. As we have previously discussed, okay, we have here the linear relationship, okay, between the vertical pressure and the horizontal pressure, okay, in a certain depth, okay. From a practical point of view, it is only necessary to determine which is the lateral soil pressure at the top of the construction and at the bottom of the foundation, okay, because the relationship is linear, okay. So the first value located at the top, you can see that there is no pressure due to the weight of the soil. So the only parameter that is acting is the surcharge equal to 10, okay. At the bottom of the foundation, the circumstances are different. As you can see here, we have the density of the soil, we have the height of the soil at that location, is 3 meters, the constant 10 kilonewton per square meter, and all of them multiplied by the active friction coefficient for earth pressure. Okay, it is very important. It is only pending two issues to be done. One of them is to obtain the resultant of forces for this volume of pressures. Okay, for that reason, we have this equation right here on the bottom left. Okay, it's like the half of the base of the pressures multiplied by the height of the trapezoid shape. Okay, and also very important to specify which is the distance of the resultant from the bottom of the foundation. This equation here, it gives us the value of the arm of the resultant measured from the bottom of the foundation. In today's post, we are only dealing with balance conditions. Let's start with a sliding condition. Okay, according to the most of the design codes or the client specifications, we also have to achieve at least a sliding safety factor equal to 1.5. Okay, the safety factor for the sliding, it is assumed like the relationship between the resistant forces divided by the sliding forces. Okay, as you can see here in this term, okay, in the numerator, we can find that the resisting forces are equal to the friction coefficient multiplied by all the weights acting against the soil. It is the self-weight of the retaining wall itself, or even the overboarding earth or soil located over the foundation of the retaining wall. Okay, for the sliding force, it is as simple as the resultant of forces due to horizontal lateral pressures that we have previously discussed in the just a minute ago. Okay. It is important to highlight that most of the critical points or the problems due to designs are based on consider the passive effect, the helpful passive effect in the design to the retaining wall. Most of the codes doesn't allow or don't allow to use this parameter, okay, and is clearly unconservative. So my suggestion it is not to use the passive contribution in order to find the horizontal equilibrium or balance of under the design of the retaining wall. Second, in order to guarantee the balance condition for any retaining wall, we have to comply with the overturning balance condition. Okay, similar to the sliding condition, there must be specified a safety factor at least equal to 1.5. Okay, and safety factor 1.5, it is we can define it as the summatory of the righting moments. Okay, divided the moments of overturning. For the writing moments, it is as simple to take moments from this point of the heel of the retaining wall and take a moment for the self weights of the different parts of the retaining wall and even for the soil located over the foundation retaining wall. Okay, the overturning moment is very simple. It is only the arm multiplied by the resultant of the lateral forces, called in this case RT. Both values, the resultant of the lateral pressure forces, also the Z, which is the distance from measure from the bottom of the foundation up to the place where the resultant is located, it is the overturning moment. Okay. It shouldn't be very critical, or this is not the governing condition, but also has to be verified in any case. Today, I would like to finish this post with a proposal of a challenge for all of you. As you can see in the screen, there is a transversal section for a retaining wall. This is a real case that was designed in Madrid, okay, in a residential residential area located at the west of Madrid. Okay, the challenge that I'm going to propose to you is very simple. I would like to know with these dimensions the retaining wall is safe against sliding conditions. Okay, for that matter, okay, we have defined these parameters of the soil to define the horizontal lateral pressure. The height of the retaining wall is 3 meters. The depth of the foundation is 0.660 meters. And one of the most important values is the width of the continuous foundation. It's 1.6. Okay, I will repeat it here, okay, for my previous explanation in Spanish. Take into account that there is also an overboarding earth or soil over the foundation, and the figure is 0.5 with the same density of the retained earth soil. Okay. um, if you like to this kind of content or this kind of post, please don't forget to subscribe and give me as much likes as possible. I would like to also to, if the content of these videos is helpful for you, please share it with all your friends, all your fellows. I know that my English could be better, but I will try to improve as every single post. Okay. And if you are more interested about engineering, structural engineering issues, please you can also visit my LinkedIn profile. Okay. So that's the end for today. I hope to see you soon. Bye bye, take care.